Welcome to the second section of the Electromagnetism module at Milestone. The topic for today is going to be about Gauss's law and its applications. So let's just really start with Gauss's law. If Gauss's law is about the fact that when you have a certain charge or you have a general distribution of charge and then you surround it with an imaginary surface that encloses this charge, then we can look at the electric field at various points on this surface that we use to enclose this imaginary surface. And Gauss's law is going to give us a relationship between the field at all of the points on the surface and the total charge which is enclosed within the surface. So let's just say that we have a box which includes a charge Q, and if we then include two charges, then that's going to create more electric fields, and we have an outward showing flux. So that's actually what we are going to discuss now. That the question is, what is the charge distribution in the box if I can only look at the electric fields? And so it's really just enough to measure the electric field. You don't need to do anything inside the box. It's enough to just measure the electric field outside the box. So, as I said, it's the flux which is really important first here to discuss. The flux is the product of the magnitude of the electric field and the surface area, which is perpendicular to this field. So when we had this box here first, and then we put two charges in it, and that's going to double the flux. And in case if we will change the box dimensions, that doesn't change the flux. So as I said earlier, that the electric flux, which we denote with the letter phi, is the electric field that's perpendicular to the area that we use to enclose it by. So this perpendicular notion is essentially here we're taking the cosine of the angle between the electric field and the surface, and we realize that this is essentially a scalar product of two vectors, the electric field vector and the surface vector. So let's again just go into a bit what we mean on the surface vector. So the surface vector is perpendicular to the surface and has the magnitude which equals to the surface. So in this situation on the left, the electric field is parallel to this surface vector. So that means that the flux is really just the product of the electric field and the surface, because the angle is 0, so cosine 0 is 1, so there is no other contribution from the cosine part. Then the other direction to do is when we have a 90 degrees angle between the electric field and the surface, so then the cosine 0 or cosine 90 will give us 0, so then in this case the electric flux will be 0. And in the other situation, we use this formula with the cosine or with the scalar product of the two vectors. If you look at the units, so then that means that we have the electric field units, which per Newton per Coulomb, and we have the units for the surface, which is just meter squared. So we have Newton times meter squared over Coulomb as the unit for the electric flux. So again, a bit more details about this A vector. N is a vector that's perpendicular to the surface, and A is the area of the surface. So the A underscore, which is this vector perpendicular to the area, and so we can also divide this into little pieces. and so still the vector notion will come in with this n unit vector, and we have the dA as the little element of the array. So what happens if the electric field varies from point to point over an area? Or the other direction, what if A is part of a curved space, not just like these planes that we used in the previous examples? So that in this case we need a more general definition, and that what we actually do is that we just calculate this flux in each of these small elements where everything we discussed is true, and we sum them up. So essentially we do an integral. We integrate these results to obtain the total flux. So it's very similar to what we did with the line integral earlier. Now this is going to be a surface integral. First we just do a summation where each of the electric fields with each of these area elements are summed up, and as the dA goes into 0, then this becomes an integral, and so we have to include the cosine, and so we just find that that's the same as taking the scalar product of the line of the area element vector and the electric field. So this leads to the definition of the flux, which is a surface integral of the electric field. So again, a reminder that the line integral of the electric field was the potential, and the surface integral of the electric field is the electric flux. So we can have another notion that if the surface is closed, then we put an extra circle in the middle of the integral sign. That just means that the surface by which we do this integral is just a closed surface. What is the flux in a sphere is a question that we can ask now, and it's very educational to go in this direction. So we calculate the flux as the electric field and the area vector scalar multiply with each other, which in this case we know that the electric field created by a charge is a radial field, right? So then when we have a sphere, that in every point where we look at the perpendicular vector to that sphere, that's going to begin radial. So that means that the angle of this A vector and the angle of the electric field vector is the same. So we can just get rid of that, and this is really just the electric field multiplied with the area. There is no vectors needed after all, because this is a special case when the two vectors are parallel to each other. So earlier we have seen that the electric field created by a charge is proportional to the charge itself and inversely proportional to the size or the distance from the charge. So we have here a sphere which has a radius of r, so that distance is going to be r squared, and then we have this constant factor. So this is the electric field part of the equation. We multiply this with the surface. So the next thing to ask is, what is the surface of a sphere? And so that we know from the geometrical knowledge from the past is that that's 4 pi r squared. So then the r squareds are cancelling each other, 4 pi's are cancelling each other, and we get that the flux in a sphere is going to be the charge divided by the epsilon zero vacuum permittivity. So that's an interesting result, because the r's, the radius and the distance, cancelled each other, and so it doesn't matter how far we are from the charge, the flux is going to be always the same value, this q over epsilon zero. So now we could make the question a bit more complicated. That is, what if you don't have a spherical surface anymore? And the answer to that is that we still have the same results. So whatever surface you have, you can go into like small pieces where you can approximate it as a spherical result and then add those up, integrate those up, and interestingly, the right side of this equation is always going to be a Q charge over the epsilon zero. So one more way that we could extend this is to add more charges. So if we have I charges enclosed in our sphere or in our non-spherical any kind of surface, which is called Gaussian surface. So if we increase the charges in the Gaussian surface, then what happens is that we have to add up these charges. So it's going to be that the numerator of the right hand side changes to the sum of these charges which are inside of the Gaussian surface. That's important. So charges which are outside are irrelevant to this case. What's important is only what is inside of the surface. So with this, we reach the Gauss's law, is that the surface integral of the electric field, which anyway is the flux, is equal. It equals to the sum of the charges inside of the electric of this of the surface divided with epsilon zero, the vacuum permittivity. We can go on and ask what if we don't just have several charges which are discrete and can be counted and have an index of I, but we have a continuous distribution of these charges. So this is something that we met earlier. With the one dimension, we had this lambda. With the 2D, we had the sigma distribution. And with the 3D, we had the rho charge density. And so that means that the right-hand side is not going to be anymore a sum for the charges, but it's going to be an integral for this charge density. And if we do the three-dimensional density, then that means that this is a volume integral of this rho charge density. And the text is unchanged, so the general statement that the total flux through a closed surface is equal to the total net electric charge inside of the surface divided by epsilon zero is still true. That point is that it's now just not discrete charges, but continuous charges. So that's essentially the content of this session. And it is the first Maxwell law, the Gauss's law for electricity. And it's a very powerful law, very powerful equation and result. So let's actually dive into how we can really use this. So let's just go into the problem solving strategies. I will keep up the equations here. So again, the surface integral of the electric field is the same as the charges inside of the surface divided with this constant epsilon zero. So we will use this if either you are given a charge distribution or if the electric field is given, and then they are asking you about the other. So, it could be that they tell you what is the electric field distribution, and the question is how does the charge distribution, or like how much charge is included in the box. Or they can give you that this is the charge distribution, and you can look for the electric field. So, as every other problem, I would suggest to start with identifying the symmetry of the system. So if you have an obviously spherically symmetric problem, then don't. Well, I mean, of course you can, but like I would advise not to try to solve it in a Cartesian coordinate system, but rather move to the spherical coordinates and use that. So after that, we have to find this Gaussian surface, and This doesn't have to be, a real surface. It just can be an imaginary surface that you imagine is there. And then you, as I mentioned, after you identify the symmetry, you choose to work in that coordinate system for the symmetry. Then we carry out the integral for this surface, and if the field is perpendicular in the point when the 5 is just a multiplication, not really just an integral, so that's a special case that we use. And if the field is tangent to the surface, then that integral will give you a 0, so there is no point of really doing any integration. And of course, if the field is 0, then the integral will be 0 too. And as always, just make sure that your results make sense. So now really just doing one example here, that the problem is that we are looking for the electric field a distance r away from a line which contains a positive charge and it's infinitely long, and so this the charge distribution is given by the lambda one-dimensional charge density. And so we know the charges essentially, we are interested in the electric field. So let's identify the symmetry first. Well, so it's a line that will have then a cylindrical symmetry, and then we are looking for the Gaussian surface. So let's just do this. That like we have this line of positive charges, and around it we have this cylindrical imaginary surface for the Gaussian surface. And so in this case, the line or this area element vector will be again perpendicular to the surface. So that means that it's radial, which actually makes us happy because then the integral is simpler, right? We have that these two things are just a multiplication, and so that means that the flux calculation, the electric field doesn't depend, it has the same value at every point, so we can just take that out and take the integral of the little area, which will then give us the full area. So that's what I just said earlier, that this is just the multiplication of the electric field and the area. So that's the left hand side of the equation. And the right hand side of the equation we know is the charge included in this surface divided by the electric field. And so we weren't really given the charge itself, we were given this lambda charge density. But so we know that the charge density just means that that we have somewhat charge inside a unit length. So if the unit length is delta L, then the charge, then then the lambda is defined to be as Q over the dl. So then by multiplying with the dl, we get that Q will equal to lambda times dl, and the epsilon zero vacuum permittivity is just carried away. Okay, so we are asked about the electric field, so there is nothing really to go inside of the electric field, that we just call E. But we do know what is the surface, so this is the surface of the cylinder, and so the surface of the cylinder is 2 pi times the radius times the delta L. So dl is really just a small part of the full wire size, since you know that the wire itself is infinitely long. And actually we could come back to what infinity really means in this case. And then the right side is still just lambda times dl over epsilon zero. So the dl's are actually cancelling out, and so we can just divide with the 2 pi r from the left hand side and get that the electric field created by an infinitely long wire is going to be lambda over 2 pi epsilon zero, and the electric field is proportional to the inverse of the distance from where we are looking at this wire. So with the infinity, we could think about it a bit. What does it really mean that we have an infinitely long wire? Because obviously in reality there are no infinitely long wires. So infinitely long or infinitely wide or whatever really just means that one of the dimensions of the system is much, much, much bigger than any other dimension. So let's just say that, like you have a wire which has 1 millimeter of a radius, and it's like 20 meters long. So 1 millimeter versus 20 meters is like a huge change. So from this aspect of perspective, if you go very close to the wire, like at the millimeter level, then if you see up or if you see down, you don't really see the end of it, and that's what they consider to be an infinitely longer wire. Okay, so here is another example. I'm not really going to solve this, but we could just look at it. This is a simpler one. We have a cube which has a side of L, and we put it into a uniform electric field E, which shows in one direction. We're interested in the electric flux through each face of the cube, and then the total flux through the cube, and it is originated with two of its faces perpendicular to the field, as we see it in the left plot, and when the cube is turned with an angle of theta, as it is on the B plot. So this is very similar to what we discussed in the beginning. If you have the electric field perpendicular to the surface, then this just gives us a zero value. If it is parallel to it, then you just multiply the two. So you just go through each of the sides and look at this thing with the with the with the A version of this plot. The B version is a bit complicated because here we don't have any more any sides where the electric field would be parallel to the surface. We do have two sides, right, where the electric field is perpendicular to the surface, so those are going to give us a zero contribution, but the rest of them will, you know, give something with this E times A times the cosine of the angle. So this problem is really just about the calculating the angles and doing a bit of a geometry here. Then this other example is just to put some numbers into the picture, not only just deal with the general variables, although physics is really about the general picture rather than the specific. But for everybody who wants to go into the engineering direction, it's good to add some numbers. So I just say that we have this 3 microcoulomb charge, and so we surround that with a sphere, and it has a radius of 0.2 meters. And so we are interested in the electric flux through the sphere. So they obviously apply the formulas from above. The electric field in this case is parallel to the surface vector. So this is just a multiplication of the electric field and the area. So you just calculate the area for pi r squared. And so r is given 0.2 meters. So you have to change the microcoulomb to coulombs, of course, so that we stay in the SI system. And you just plug these things into the formula and you get the flux. Okay, so this is a question which I'm going to answer. We are looking for the electric field caused by a thin, flat, infinite sheet, which has uniform positive charge per unit area as sigma. So this is a second, next dimensional problem. Earlier we had an infinite wire, now we have an infinite sheet. So we follow the problem-solving strategy. We have a system which is 2D, and we want to have a surface which is three-dimensional, and so it makes sense to use the cylindric um, surface for this. And so the fact that we have an infinite sheet is again helpful, because that means that however up we go on this sheet, we will have the same kind of charges as however down we go on this sheet. So the electric field created by those will actually cancel each other, and so the only electric field that stays is what's in the middle of this plane, and so that's where we have this Gaussian surface, Gaussian cylindric surface here. And we should also say that like this surface has a plus minus d distance from the middle of the sheet. Okay, so using the symmetry principle, we realize that the only electric field that stays is the electric field through here, and so everything which is on the side of the cylinder is cancelled by the electric fields created on the other side of this plane. So we are having two contributions to the electric field, one on the plus d side or minus d side, and on the other on the minus d side or the plus d side, depending on which direction we call minus. So when we take the flux calculation with the integral, we have two contributions, the E times the A on the left and E times A on the right. So that means that we evaluate the electric field at the d distance, and we multiply with the area of the circle in the end of the cylinder, which is 2 pi times r squared. And we again have a circle on the right side of the cylinder, so that's again 2 pi times r squared, and we evaluate the electric field at the minus d location. And again, just thinking about the symmetries of the system, it cannot be that the electric field would be different on right side than it is on the left side. So the value of the electric field at D is the same as the value of the electric field at minus D. So that means that we can just add these two things up, and the final result is 2 times the electric field times 2 pi r squared. And then the right-hand side of this equation is the sum of the charges divided by epsilon 0. So similarly to the line example, we are not given the charges, but we are given the density. We get the charges back by integrating it out. So this means integral of surface integral of the sigma, but because sigma is uniform, the surface integral really just means a multiplication of sigma times a. So what is this a now? Well, it's the same a that we used earlier, but not actually the same one. So this is now the circle which is cut by the plane and the cylinder. So the circle which is in here, but it's the same circle. It has the same radius, so the formula will be the same. So the right hand side of the equation is sigma times 2 pi r squared over epsilon 0. If you put these two together, then we see that there is the same area area value on both sides, so you can divide with that, and we are interested in the electric field, and so we divide with the 2, and by this we get that the electric field is sigma times 2 epsilon 0. Similarly to the line example, we notice that there is no r included in this result. So that means that it doesn't depend how far you look at this electric field created by this plane. It's going to be always the charge density over 2 epsilon 0. This example is very important because we can use it in this second or third example where you have two plates now. So we have two large planes. Again, we could say that they are, infinitely big, and both of them have the same charge, but they have opposite sign. So there is a plus sigma and there is a minus sigma, and we are interested in the electric field created by these two plates. Well, actually, all right, I said earlier that we have infinite plate. So in this problem, we were not given infinite plate. In this problem, we were given two large plates. So then the electric fields will look like that they are somewhat uniform in the middle, but then as you go to the sides, there will be these fringe effects, which are complicated to actually model. So what we are going to say that, okay, if these plates are big enough, and we are close enough to the system, that means that we can consider them to be infinitely big, and so we will actually live with this assumption, or you could also just think that we zoomed in a bit. So we have three regions, and we know that one plate creates the sigma over 2 epsilon 0 electric field. So the three regions are that we are, let's say right or the top on the top of the top plate, above the top plate, or right to the right plate. We are in between the two plates, and we are like left or bottom to the bottom plate. So in the A region, we know that like the distance doesn't matter. The electric field is always this 2 sigma over 2 epsilon, and so we also know that it is pointing outwards for the top plate, and it's pointing inwards for the bottom plate. So that means that these two things will actually cancel each other, and the same situation is true for the other region, the C region. Those are also cancelling each other. We could also look at the picture that the electric field created by one of them is in this direction, and the electric field created in the other one is in the other direction, but same magnitude, so they are cancelling. That's also cancelling, and then just the B region is what survives. In the B region, we have an electric field which is pointing outwards, and then the other one is pointing inwards towards the bottom plate. But that just means that they are actually showing in the same direction. As we see, epsilon or E1 and E2 are showing in the same direction. Both of them have sigma over 2 epsilon magnitude. So if you add up the two sigma over 2 epsilon, you get that the electric field created by these two plates have only non-negative or non-zero values in between the two plates, and that value is going to be sigma over epsilon constantly. And with this, we end this lecture. And so I guess hopefully you have already noticed that what we described here is a very good initial modeling of a capacitor. So next week we are going to discuss capacitors, capacitance, putting capacitors into series, parallel, and serial, and then we will also discuss how metals work and insulators and so on. So please ask your questions and in the comment section, and don't forget to like the video if you wish to. See you next week. Bye bye.